Alright, welcome to Algebra 2, and we're going to jump right into the class with Chapter 1, Section 1, Properties of Real Numbers. And to get started, we're going to go to our first objective, and our first objective is graphing and ordering real numbers. Alright, so there's real numbers and there's imaginary numbers, and imaginary numbers, we're not going to deal with those today. We'll talk about those later on in class. But real numbers, really just anything that you can get on a calculator. All the numbers that we typically deal with are broken up into a couple different sets. So the first one being natural numbers. So the natural numbers, otherwise kind of known as our counting numbers, such as 1, 2, 3, positive, no zero. All right, so zero comes in when we talk about our whole numbers. So whole is 0, and then all of our counting numbers. So 0 plus the naturals. All right, let's add in integers. So integers, we're just adding on here. We've got 0. We've got our whole numbers. But then we have our, and we'll introduce the phrase here, opposites. We have our negatives. So the opposite of 1, negative 1. The opposite of 2, negative 2. All right, so no decimals at this point, but just nice round numbers, but positive, negative, or 0. All right, we're getting in here to our rational numbers. Let's see if I can erase this. Doesn't look like I can, so I'll scratch that out. All right, so rational numbers, anything that can be written as a fraction. All right, so 5 halves works. But it also includes all of these numbers from up here, because we could do something like 5 over 5, which reduces down to 1. All right? And to be a rational number, you either have to write it as a fraction, or if it's a decimal, it either needs to stop, like 1.3, or it needs to repeat forever. 1.33333. We can write that as 1.3 with a little bar over the top. 1.3 repeating. All right, so we call this terminal, and we call this repeating decimals. So if you're either a fraction, a terminal, or a repeating decimal, you're a rational number. And then we come to the end of the line here, and we've got our irrational numbers. Irrational numbers, the fractions, I'm sorry, not fractions, the decimals that we cannot write either terminal or repeat, and they're going to go on forever. So I bet you can think of the most famous one of the most famous ones, being pi, 3.14159. It doesn't stop. It doesn't repeat. It's going to go on forever down the line. All right? Square roots, unless it's a square root of something pretty, like 25 that comes out even as 5, okay, that is not irrational. That would be rational. But how about something like the square root of 5? All right, if it doesn't have a nice pretty square root, it's also going to be irrational. All right, so those are our different sets of numbers. We can view them kind of as a set here. And again, this is all in your textbook, so you can read along with me. The real numbers, all right, are the set of everything. Everything that we're going to deal with so far is a real number. And inside of those, we have two different sets. So we'll start by looking at the rational numbers. All right, rational numbers, the most broad category, include fractions, include decimals, include negatives, include everything except for those decimals that don't repeat and don't stop. All right, so then we simplify it a little bit more. We've got integers. An integer is a rational number. All right, but an integer is a rational, but a rational might not be an integer number. All right. So then we have our whole numbers. We're going to just be talking about 0, 1, 2, 3. And then the most simple of all, just our counting natural numbers, 1, 2, 3. I bet you can guess what's in the other box over on the other side. Those are our irrational numbers. So our square roots, our cube roots, our pies, our decimals that go on forever. All right, so make sure you've got that filled in on your worksheet. And if you need to pause, do that. Otherwise, we're going to move on. All right, so let's go over our example problems here. Many mathematical relationships involve variables that are related to amusement parks. Which set of numbers best describes the values for each variable? The cost C in dollars of admission for n people. The cost of admission is a rational number, such as 725, and the number n of people is a whole number, right? So people, you can't have a fraction, right? Could this be just counting? Just be natural? I guess it could be if you're assuming that at least one person showed up. But if you're allowed to have 0, then we have to go back to our whole numbers here. All right? Now, obviously, we need money to stop after 2 decimal places here, right? So since it stops, but it can be a decimal, then we're talking about a rational number. Since we don't know how much money we're charging for this amusement park. If we knew it was $8, right, then it would be a natural. And for the person that's being charged, they're being charged -8, right? -$8 is what they're worth now because they had to spend it. That would have to be an integer because all of a sudden we're involving negative numbers. All right, how about the maximum speed, s, in meters per second of the roller coaster? So maximum speed has to be positive, right? So if we're talking about that, meters per second, you would think, all right, positive, so we're talking probably a rational number here, but meters per second is going to be irrational, since speed is calculated with a formula using the square root. All right, if you remember speed from last year. If not, page 845. Those extra skills has some formulas that we can go into. All right, but you get the idea here again. Square root is going to be an irrational number. All right. How about the height of the roller coaster? All right, so height has to be positive here, but could it be a decimal? Sure, it could. 25.2 meters maybe. All right, doesn't have to be a whole number, so we're talking rational here. All right. All right, and lastly here, let's talk about the park's profit or loss in dollars and for each week of the year. All right, so week, obviously, there's 52 weeks in the year, so that's natural. And profit or loss could be a decimal. We make $1,001.23, so we're talking about a rational number here. All right, so I would like you to pause the video and try understanding check for this first example. It's out of the textbook. All right, if you're ready to go, let's try example 2, graphing numbers on the number line. All right, so we're going to graph the numbers -3/2, 1.7 repeating, and √5. So just a little review, a little refresher on number lines here. Remember, if we're going to draw a number line, probably the fastest way to do it is drop the 0 right in the middle and go tick marks evenly spaced off of that, which you'll see here in the drawing, a lot neater than mine. But if we look at this, obviously negatives are going to the left of 0, posits of negatives. And if we're going to the right of 0, we've got our positives. All right, and so we'll take a look at approximately where these numbers are. -3/2 is -1.5, so right in between 1 and 2, negative. 1.7, a little bit closer to 2 than it is from 1, so approximating there. And √5, you would have to put in your calculator. I guess you could do this in your head because let's review this. Square root of 4 is 2. Square root of 9 is 3. So is √5 closer to √4 or √9? And 5 obviously closer to 4. So as you can see here, it's a lot closer to the 2. And it comes out to about 2.2 here. Okay. Quick check on this one. -3/2, this would be rational. 1.7 repeating would be rational because it repeats, but then the square root would be irrational. Since it's 2.2, that decimal doesn't stop. If you look on your calculator, it's going to keep going. All right, your turn. Try problem understanding check 2. All right, if you're ready to go, let's try example 3, ordering the real numbers. Let's remember our less than and greater than signs. So negative square root of 0.25 All right, so if we take a look at that, if we punch that into our calculator, we could check that that is actually negative 0.5, but kind of beside the point here. We want to also look at negative 0.01. All right, so 25 is obviously bigger than 1. So if we were comparing these without the negatives, we would say 25 is bigger. Remember, the opening points to the bigger number, right? But since they're negatives, we flip it. 25 is the smaller number. If you owed me $25 versus owing me $1, you'd much rather owe me $1. So, opening towards the bigger number. You're up. Give it a shot. Example 3. All right, let's move on to our second objective here, operations with real numbers. And so we've got a couple vocab words here for you to add in on your worksheet. So opposite and additive inverse mean the exact same thing. All right? So the opposite or additive inverse is just putting a negative sign onto whatever number you have. All right? So if we have 5, our opposite is negative 5. If we have negative 10, then it becomes negative 10, which, as we all know, turns into just regular old 10. All right? So we're just flipping the sign to get our opposite. All right? And if we ever add up our opposites, we need to get 0. 5 plus negative 5 gives us 0. That's what this line here is saying. All right? Let's talk about the reciprocal or multiplicative inverse of any non-zero number. Let me get rid of the writing here on the screen. Okay? All right, so the reciprocal is flipping it over 1. So the reciprocal of 5 is 1 over 5. The reciprocal of 1/3 is 3. And then fractions just get flipped over. The reciprocal of 2/3 is 3/2. And if you are ever to multiply these together, you end up with 1. Multiplying reciprocals gets you 1, which we use a lot in algebra, algebra 2, pre-calculus, all the way up. So we want to remember that one. All right, so we'll take a look at our fourth example. Let's find the opposite and reciprocals here. So the opposite of negative 3.2, let's flip that sign, positive 3.2. The reciprocal is going to be 1 over negative 3.2. All right, and you can put that negative out front. Opposite of 3/5. Negative 3/5, reciprocal, flip it over, 5 over 3. Give it a shot, example 4. All right, let's sum a few things up here with our properties. You've seen this is a review from Algebra 1. Closure property of addition, a plus b is a real number. So if you have two real numbers to start with and you add them, it's still real. And the same works for multiplication. If you have two real numbers and you multiply them, they're still going to be a real number. All right, let's remember what commutative means. Think about your commute to school. You go one direction from home to school. You turn right back around at the end of the day. You do the exact same trip in reverse. All right, that's what the commutative rule is. A plus b is b plus a. 5 plus 3 is 3 plus 5. Flip it around. Same thing works for multiplication. Okay, 5 times 3 is the same as 3 times 5. All right, associative means you can move the parentheses around. Okay, it works for addition and multiplication. The order does not matter. Identity, if you add 0 to anything, it stays the same. And this is the first one where it switches up. Multiplication looks a little different. Not multiplying by 0, but multiplying by 1 to stay the same. All right. Inverse, right? We're talking about our opposites here, adding to 0, and our reciprocal multiplying to 1. So what we just talked about for our inverse properties. And let's talk about our distributive property. If we take a times b plus c, this is going to distribute in, and we'll get a times b plus a times c. So a little review from Algebra 1. Let's take a look at which properties are being illustrated here. So 6 plus negative 6. Remember, we're canceling things out here. This is the opposite, so this is the inverse. If you said inverse, nice guess. Not guess, good job. And right here, let's see, we've got negative 4 times 1 minus 2 is the same as negative 4 minus 2. What changed? The only thing we lost here was the times 1, right? Timesing 1 is not really doing anything, so that's the identity property. Timesing by 1 is the same thing as not really being there at all. We can always add in a times 1. Time for you to try it on your own. Try the understanding check, example 5. All right, last one. Here we go. Let's bring this thing home. Absolute value of a real number is its distance from 0 on the number line. All right, so we're just looking at its value. We don't care about its sign. So absolute value of negative 4, 4, absolute value of 0, 0. And then let's look at the slightly harder one here. Absolute value of negative 1 times negative 2. Okay? We're going to work the insides first and then do the absolute value. Remember, from parentheses, we work inside out. So this is the absolute value. Negative 1 times negative 2 is positive 2. And then the absolute value of that stays the same at just 2. All right? So we simplify first, and then we do the absolute value. And so in the book, they've got a nice drawing there on the number line for you, just showing that negative 4 is 4 units away from 0. All right, kind of giving you a graphical look at absolute value. All right, so that's it. Make sure your worksheet is complete and ready to go. Any questions, I will be available for you in class tomorrow.